Now, part of why I wanted to talk about machine learning was the following. Typically, when you hear about machine learning, you hear about it from one of two places. You hear about it from vendors. And when you look at the vendor white papers, they claim that machine learning can solve world peace, it can cure cancer, it can help with space exploration and a whole bunch of other things that probably it can't quite do. On the flip side, if you learn about machine learning from academic papers, you'll get maybe a more balanced view, but typically that view is restricted to what happens inside of a very nice, clean lab environment. It doesn't tell you what's going to happen when you try to take those same ideas and apply them to the real world. So my goal was to provide a bit of a balanced view. Now, I call the talk Cybersecurity, Boon or Boondoggle. This is what happens when technical folks spend too much time with the marketing team. Hopefully the title makes some sense, but the idea is to provide a more balanced view, the good, the bad, and the ugly of machine learning. So if you are thinking about using machine learning, whether you're trying to implement it yourself or you're evaluating a third-party vendor solution or capability, the hope is to give you some additional context to help you make an intelligent decision about exactly what machine learning can provide you with and whether or not it's something that you actually want to use within your own products and services. So with that, let's get started. I'll break the talk into three parts. So I'll start off by giving you a broad stroke overview of machine learning. This is really to put everyone on the same page. Think of it as a 10-minute crash course in various aspects of machine learning designed to give you just enough information so you can understand the rest of the presentation. The second thing I'll do is I'll talk about how machine learning can be applied within cybersecurity. Now, this won't be that complicated once you understand what machine learning can do. And the third part, which is really where I'll spend the bulk of my time, is talking about best practices and pitfalls. And they kind of go hand in hand. If you find a pitfall in the implementation, that typically suggests a corresponding best practice, or maybe what I call a better practice, because it's really hard to define sometimes what best means, since it's a constantly evolving area. So with that, let's go ahead and get started and talk about machine learning in some more detail. Now, machine learning, according to Arthur Samuelson, who was an early pioneer in artificial intelligence, is a field of study that gives computers the ability to learn without being explicitly programmed. Now, I think the most remarkable thing about that definition is that it was proposed in 1959. So machine learning as a field has been around for more than half a century, even though it seems like it's gotten very popular in the last couple of years, especially as you start to look at what's going on in the vendor community and beyond. But the field itself is very rich and has a broad history. More concretely, in technical terms, what it involves is developing algorithms that can draw inferences from and make predictions based on data. So the key word here is data. It's really about being able to find the right data sources, developing techniques to extract insights from those data sources automatically, then apply those insights to new instances that you haven't really encountered before. Machine learning itself has had a rich history. It's evolved from other areas of computer science, so things like computational learning theory, pattern recognition, data science, and so on and so forth. And over time, we've seen subtle differences in certain terminology and nomenclature, but ultimately, I think the ideas are now becoming much more mainstream, and the goal now for the practitioners, how do you actually take some of these ideas from the lab environment and make them work in real life? And I'm going to focus a bit on that. Now, the reason people like machine learning, the reason it's gotten a lot of popular attention, is it enables you to get some degree of automation, because you can actually try to learn automatically from data. Machine learning in theory should be unbiased because it's based directly on the data source you're looking at. You're not introducing any human biases into what the actual outcome is going to be. And then finally, there's an element where you can try to improve over time. So as you get new data coming into a system, the hope is that you can use machine learning techniques to evolve automatically based on new data, which is obviously very relevant in a security context. So for security specifically, machine learning is interesting because it enables some level of automation, so can we come up with models automatically for being able to identify malicious activity? And more importantly, can we enable those models to evolve over time as we get new data about attack behavior? Because today we're not dealing with your typical static adversary. In cybersecurity, we deal with a sentient adversary who's going to try to modify what they do on a regular basis. That's the theory. In practice, it's actually a lot more difficult to make some of this stuff work, and that's really going to be the focus of the second half of the presentation, as you'll see. Now, machine learning in general involves three parts. I'm labeling these things explicitly because I think it helps us understand some of the pitfalls and best practices. So the idea is not to kind of beat a dead horse if you already know what machine learning is, but by talking about machine learning in general, you'll see exactly how I'm thinking about it and how you can start to apply it, or where you can avoid some of the mistakes that I've seen happen in the past. Typically, there are three phases in machine learning. You start off with data. Very important to kind of call this out. From that data, the goal is to generate a model. And that model is something that's going to basically be something that's more compact, an easier representation, that's adequately or well explained by the data. And the idea is, can we take that model and apply it to new instances? Can we draw inferences from the existing data and use that to reason about things we haven't seen before? Now, in practice, the way it works is your model typically has a set of parameters. So you can think of maybe the model as a set of equations, and there's some unknowns. And the goal with a machine learning algorithm typically is to figure out the values for those unknowns that optimize the behavior of that model with respect to the data that you started with the hope being that if you do it correctly, you'll be able to then apply that model to new instances. And so it becomes an optimization problem. Can I fill in those question marks with actual parameter values? Now, given that, what ends up happening is that there are different aspects of machine learning. I want to point out one thing about what machine learning is not, because people often confuse machine learning and artificial intelligence. They use the terms interchangeably. Really, artificial intelligence is a broader field of which machine learning is one subset. A great example of something that was artificial intelligence, but not really machine learning, was the famous chess match between Garry Kasparov and Deep Blue. Deep Blue was a supercomputing chess platform that was developed a number of years ago in the 90s, and it was the first computing platform that could beat a world chess champion in a match. And that was a pretty profound moment, I think, in the history of AI, because it was the first time that a world champion in chess had actually lost in a match, a 6-game match, to a computer. The match was actually pretty close. It was tied up until the last game of the match. Then Kasparov made a really simple mistake in the early stages of the last game, and essentially, I think, psychologically somewhat crumbled in the last game, which is something that computers don't do. They don't cave under psychological pressure. But what's interesting about Deep Blue is that it's not a machine learning system. The way it was developed is that the team hired a group of grandmasters and strong players, and those players developed an evaluation function, a function that could look at a chess position and determine really who was better, who was worse, and how much better or worse they were. So they could look at a chess position and say, okay, white's better here by this much, black is better here by this much. And the idea was that Deep Blue itself would evaluate a number of different positions. It would consider possible moves that it could play from a given position. It would consider possible responses. It would consider responses, those responses, and so on and so forth. It would end up with a series of positions. It would evaluate those positions and then work its way backwards to find out what the right initial move would be. Now, given that, this is not really a machine learning approach. This is an approach where a human team of grandmasters came up with an evaluation function, and the computer was just used to leverage its computational power to apply that evaluation function as many times as it humanly could. And for a long time, that's how chess evolved. Chess has really gotten better on the computer front, not because there's been some fundamental advance in the algorithm, it's because they can throw more computing power to evaluate more positions. If, on the other hand, you were trying to build a chess playing program using machine learning, you'd do something different. You'd probably start off with a history of games that have been played, the winners of those games, and then let the computer figure out the right set of rules that could potentially be used to improve over time. Deep Blue did not do that. Deep Blue literally had the team coming up with the function, and then in between every game of the match, the team was adjusting that function based on what it learned about Kasparov's play. So it was much more of a combined human-computer effort than a true effort to learn from data on its own. Now, the next thing I want to talk about are the two different aspects of machine learning at a high level. So we tend to have supervised learning and unsupervised learning, and there are other branches of machine learning, but most of the time you'll encounter one of these two. Supervised learning is about being able to learn from labeled examples. So for example, let's say you're trying to build a machine learning system for determining whether or not you should give a loan applicant a loan. So what you're really trying to do is build a system that can determine the likelihood that person will default on their loan. So in that case, your labeled data might include historical loan applications, as well as information about whether that candidate ultimately ended up defaulting on their loan. And if you find that there's a certain set of attributes that led to a higher likelihood of default, then you can bake that into your model, and then the model can be applied to new loan applications to determine whether or not that applicant should be approved. That's kind of at a high level. What ends up happening at a slightly lower level, and this is really important because it's going to help us understand, again, best practices, is that typically we don't just start with raw data and develop a model. There's typically a step in between of being able to extract good features from that model. We call that problem feature extraction. That typically involves a human expert who says, okay, well, if you're looking at a loan application, there's a few things you should look at carefully. So for example, you might want to look at the size of the loan. You might want to look at the number of years the person's been employed. You might want to look at their marital status. The idea is maybe each of those attributes in isolation tells you whether or not the loan should be given. So for example, if somebody's worked for many, many years, they're probably a better candidate for avoiding a default. If they've got a high income relative to the loan size, they're probably a good candidate. If they're married, they may be a better candidate because they have two sources of income potentially, and so on and so forth. And then the goal of a machine learning algorithm is ultimately to take all those attributes and figure out the most intelligent way to combine them within certain restrictions to lead to a good outcome when it comes to predicting whether or not a new person will ultimately default on their loan. So hopefully that application makes some sense. I wanted to provide a generic application, and we can talk about specific applications of cybersecurity. But before I do that, I want to talk about one other aspect of machine learning, which is unsupervised learning. Unsupervised learning is about being able to learn from examples that may or may not have labels associated with them. Typically, this is a field of machine learning that involves trying to understand structure in data. So you can see I've kind of created a data set, synthetic obviously, a bunch of points mapped on two-dimensional space, and what you can start to see is those points have some kind of structure associated with them. They really fall into three different clusters. And that kind of tells you something about the data. So for example, if some point were to appear on that data set outside of those three clusters, that might tell you that, hey, that one point is somehow anomalous. It's really different from what we've typically seen. Or if you see a point that falls into one of the clusters, you can start to infer that its behavior or something about that point is similar enough to the other points that the attributes of those other points could then be transferred potentially to that new point that you're looking at. And for the most part, when you encounter machine learning in a cybersecurity context, you'll typically hear about either supervised learning applications or unsupervised learning applications. And there are other fields of machine learning. There's semi-supervised learning and a bunch of other things. I won't go into that today because I think that's too much detail. But hopefully this gives you a feel for what's going on when machine learning is being applied. So how do we apply machine learning to cybersecurity? First of all, when you think about it, most security applications involve some form of classification of behavior on a transaction. Is that transaction good or bad? Whatever that means. So for example, if you're trying to do a spam filter, you might look at an email message and say, hey, is that email message good or is it spam? And you might look at certain attributes of that email, like some of the words that are being used, the fonts, and maybe the size of the message, information about the sender, the domain name, etc. You could also apply this concept to online fraud. If I see a given transaction, is that transaction legitimate or is it fraudulent? And by the way, when you look at the credit card companies, they've been applying machine learning for decades to solve this exact kind of problem by looking at attributes of the transaction, such as what's being bought, the time of day, the past behavior of that particular individual, whether or not that transaction is somehow anomalous. So for example, if you suddenly buy a plane ticket to Africa and you've never traveled before, you might get a phone call from a credit card company. That actually happened to me once a long time ago, so I remember that vividly. They may look for other things like, is there something suspicious about the transaction behavior? Like for example, if you buy gas at the same time as buying a Dell computer, that actually also happened to me a long time ago because my wife was buying gas while I was buying a computer. We both got a phone call. So they're looking for things of that nature, things that don't make a lot of sense, but that somehow would be indicative of fraudulent behavior. Malware is another great example. So we're seeing a lot of companies now that talk about next generation antivirus. They're applying machine learning to be able to detect whether or not a file is malicious. And by the way, it's kind of funny because I don't think of this as a next generation idea. Actually, all the major antivirus companies have been doing this for about 7, 8, 9 years in production. But I think what's happened recently is machine learning has become such a popular concept that we're hearing more about the how in terms of what's happening rather than the why and the what. Also being able to detect malicious URLs, malicious IP addresses, you can apply machine learning to that problem. So you might look at things like, how long has a domain been around? What do we know about the who is information? What do we know about the geography of the server on which a particular website is hosted, and so on and so forth, to understand whether or not some piece of traffic might be malicious. So those are some of the attributes you might look at. Then the goal with machine learning is to take those attributes, make sense out of them, and then make predictions about future instances. So hopefully that makes some sense. You can also apply unsupervised learning to cybersecurity. In that case, you might look at things like whether or not you see abnormal behavior. Do I see a user suddenly engaging in a traffic spike? So we saw this with Shape. They actually did a really good job of being able to show that we're seeing weird traffic because all of a sudden we're seeing a situation where a user or a particular website is seeing weird traffic patterns that aren't explained by typical behaviors. You might be able to look at things like an increase in failed login attempts. You might want to look at whether or not a user is accessing resources they wouldn't typically access. These are the kinds of things you might look for if you're trying to find an attack. Now, what I want you to do for a moment is kind of suspend judgment about whether these approaches will work in real life. I'm going to get to what I think some of the pitfalls and strengths are, but this is typically how we see machine learning applied when you're doing it for cybersecurity. and specifically in this case, how we see unsupervised learning applied in a cybersecurity context. So given that, what are some of the challenges, pitfalls, and what I call better practices for machine learning? This is really where I think the most interesting part of the talk is. The rest of the work was really there to give you, did I lose audio or? Okay, perfect. The rest of the talk was really about giving you some of the foundations. This half is going to be really about being able to understand how to apply those foundations correctly and what I see as some of the challenges in being able to do that. So this is really the part where I start talking about the boondoggle, right? What actually goes wrong when you try to make these things work in real life. And by the way, so just by way of background, I've had a chance to work on machine learning now at I think 4 or 5 different companies. I kind of lose track. But it started off with Symantec a number of years ago, and I see a whole wall of yellow, so it's kind of good to see some old colleagues. But the cool thing there is that, you know, over time we kind of learned the hard way what would and wouldn't work when you all of a sudden take something that looks really great on paper and produces a really beautiful graph, and you try to put it to 200 million users. And you know, you don't want to get that wrong on day one. So the first thing, and this is a really subtle point, is that it has to start with good data. It's amazing how many people forget this, right? That's why I kind of talked about the process of being data, then features, then classifier. Because if you don't start with good data, nothing else matters. Machine learning is garbage in, garbage out. I've seen many cases where people will come up with a training set. They'll develop a model based on the training set. Then they'll try to apply that model on real world data that looks nothing like the training set that they originally trained on. And sometimes it's very subtle. I mean, it may be like, they may have had the best of intentions, but they may have been using like a black box tool or an existing machine learning library. They weren't paying attention to what was happening inside the library. And sometimes the libraries are manipulating some of the training data as part of training, and you may end up getting a different result. And I've seen this gotten catastrophically wrong in so many cases that I'm just pointing it out, even though it almost seems somewhat obvious. Ultimately, with machine learning, you have to write to ask questions, just like you would in data science. It's not about looking at data and making inferences. Typically, there's a phase in which you look at that data and you say, what are the right questions to ask? What are the right things to look at? And then based on that, you come up with intelligent inferences. So don't think of machine learning as a panacea. If it looks really beautiful on paper, you've still got to be very careful to ensure that when you put it in real life, you're mimicking what you saw on paper earlier. And that, I think, is one of the grandest challenges with machine learning in practice. The second challenge is people get obsessed with the classifier. I mean, I've never seen, you put an engineer in front of a good library, and they'll start tweaking every single aspect of the classifier. But to me, that's the least important part of machine learning. If you're talking to a vendor and they're talking about how many layers in their neural network, or they're talking about the latest techniques that they're using, that's all fine and good. But again, it has to start with data first, then coming up with the right features associated with that data set, and then and only then do you care about the classifier. Now, it turns out that if you've got the right data first and the right features, here's a secret. It almost doesn't matter what classifier you choose. They all perform within like a fraction of a percent of each other. And most academics who focus on this topic, they're looking for like 0.1% improvement, or maybe like a 1% improvement to publish a paper. In practice, there may be reasons to go with a simpler classifier for debugging or being able to deal with it in the field, and really focusing on making sure your data's good and your features are good. So I see that mistake over and over again. You'll hire a cadre of PhDs in machine learning, and they never have one domain expert on their team to say, these are the features that are most relevant. Like, here's a good example. Let's say you're trying to develop a machine learning system that tries to classify whether or not a given URL is likely to be malicious. Okay, if you do all sorts of crazy things with URL, you can manipulate it 10 ways till Sunday. But if you ask any analyst in a security operations center what's the first thing they do when they see a URL, they do a whois lookup and they figure out how long that domain name's been around. That's probably one of the strongest indicators of whether or not that domain is malicious. But if you're not looking for that, if you don't know to look for that, if you only are thinking about the data science part of it, you may miss one of the most simple features that gives you a huge performance boost. And that's why it's really critical to focus on those 3 layers in order. Start with good data, then focus on features, and then worry about your classifier. And I'm really belaboring this point because most people do it the opposite. They really focus on the classifier, they tweak the hell out of it, but they never think about what's happening at a higher level in the stack. The next thing is that security has what I call a class imbalance problem. Most things we see in real life are not malicious. Most times that a credit card transaction is made, it's benign. Most files on your laptop are not malware. And this almost seems obvious, but it actually has a huge implication for machine learning systems, because machine learning systems have to sidestep all those legitimate instances on their way to finding that one illegitimate instance. Which means that the problem of false positives is huge. It is a tremendous, I think it's the number one thing if you've got to focus on minimizing in an in-field setting is how do you minimize that false positive rate? How do you start to think about the right metrics that matter? And it turns out that class imbalance becomes a really critical measure because if you don't think about class imbalance, the odds are that you're not going to be able to interpret your metrics correctly and know whether or not you're performing well. So let's talk about some of those metrics. Typically, in machine learning, there are two very high-level metrics that are applied in cybersecurity. The one metric is what I call the true positive or detection rate. This is the rate at which you detect malicious stuff. So for example, if you have your data set that you're trying to evaluate, you look at all the things that are malicious in that data set, and you try to find what percentage of those actually malicious things were classified as malicious by your machine learning algorithm. That's a detection rate. On the flip side, there's the false positive rate, which is the rate at which you might alarm accidentally. How many times are you taking something that's otherwise legitimate and calling it bad accidentally? I mention these two metrics together because you've got to look at them in conjunction with each other. A lot of people will tout incredible true positive rates. They'll tell you that, you know what, I'm getting 100% detection rate, but they'll never tell you what the false positive rate is. And you've got to look at that together because you know what, I can build a fantastic classifier with 100% detection rate. All I'll say is everything is bad. That's got 100% detection rate. It's also got a really crappy false positive rate. Now, I know this sounds almost like brain dead, but at some level, if you take a step back, you'll see a lot of vendors never talk about the other aspect of their metric. And oftentimes, it may be very, very bad, especially when you couple that with class imbalance. And I'll give an example of that in a moment to make that point really, really crystal clear. And so in general, there's a trade-off between the true positive rate and the false positive rate. As you get more aggressive to detect things, you're more likely to get false positives. So what you're typically trying to measure isn't just a true positive rate and false positive rate on its own. What you're trying to understand with machine learning is a trade-off that you get between them. A good machine learning algorithm will give you a favorable trade-off. It'll give you a big bump, potentially, in the true positive rate for a modest or maybe small increase in the false positive rate. And the way we do that in practice is we try to take the true positive and false positive rates that we get from our classifiers. We typically graph them. We call that graph the ROC curve, the receiver operating characteristic curve. And we try to look at the area under that curve as a measure of how well that classifier is giving you a trade-off between true positives and false positives. And that's probably a better metric to look at versus just an individual true positive or false positive rate, because it could totally depend on the application you're concerned with. So now let's look at a more detailed example about why I think false positives don't tell the whole story, why you've got to look at everything together. Suppose you're reading an academic paper, and I've read academic papers that say something like this. They go, you know, we develop a system with 100% detection rate, 100% true positive rate, and a 0.1% false positive rate. Now, that sounds pretty good, right? Those numbers sound pretty compelling. If I saw a paper like that and I didn't know any better, I might say, well, yeah, that sounds like something I should implement. And by the way, I've never seen a paper with these good numbers, so keep in mind that this is pretty much a dream scenario in a lot of academic papers. What happens when we put that in real life? So imagine I've got a bunch of instances, which are kind of yellow, and there's one malicious one in there. That's the one that's really, really bad. The rest of them are otherwise benign. Very typical scenario. If you're looking at credit card transactions, most are good, one might be bad. If you're looking at files, for every 10,000 maybe legitimate files on a laptop, there might be one piece of malware. In fact, about 10,000 to 1 is a pretty good ratio that seems to work pretty well across a number of different domains in which machine learning is applied. It's not perfect, but it kind of works for this example. So imagine that for every 10,000 things you see, there's maybe one malicious thing in there. Now let's apply this perfectly amazing classifier to this scenario. If I did, then let's say out of all these 10,000 transactions, okay, I'll catch the illegitimate one because I have a system with 100% detection rate. However, that system also has a 0.1% false positive rate, which means that 1 out of 1,000 times, I'm going to call one of those yellow dots red. That means if you're sitting inside of an incident response center or a SOC, or you're looking at alerts or whatever it is, you're going to get another 10 alerts to go with that one alert that you started with. What that means is that for every 11 alerts you see, only one was actionable. So 90% of your time were spent chasing false leads. The reason I'm really belaboring this point is that when you think about it for a moment, the numbers I started with, I said 100% and 0.1%, those numbers sound really fantastic at a high level. When you work out what that means in practice, it turns out to be really dangerous. It turns out to be something that actually probably is untenable. If I told you I'm going to sell you a technology where you're going to spend 90% of your time chasing false stuff, you'd kick me out of the room in about 5 seconds, right? There would be no hope of being able to get that done. And yet, it's really about phrasing. I started off by talking about metrics in a very positive light. When you work out what those metrics mean in practice, it turns out to be very negative if you're not careful about how you apply them. So the moral of the story is think about your metrics really, really carefully. I give you just one example, and there are many others. For example, not every false positive is created equal. If I had a false positive on a popular file, let's say svchost.exe, not that that's ever happened in real life, some of you know, that would be much worse than a false positive on a file that has never appeared anywhere, or maybe on one system out there in the world. If I had a false positive on a critical business application in an organization, maybe not be a very popular file, but if it takes one system down and the company can't conduct business, that's a huge issue. So you've got to consider that not every false positive means the same thing, and it totally depends on context. The second thing is that not every true positive is created equal. Okay, some people may not mind certain things, or maybe they're okay with adware being on systems, but they really care about info stealers for other reasons. So you have to be careful that when you look at machine learning and try to translate that to what it means for an organization, you've got to account for some of these factors in terms of what you're trying to achieve with your machine learning solution. The third thing, and this is kind of funny, maliciousness is subjective. You know, I've talked to customers where they don't mind an adware toolbar. I don't know why they don't mind it, but somehow they don't mind it. Maybe they want to buy adware. Maybe they want to buy those fake Rolexes. Maybe they want to get spam. But the reality is that this is not always a clear-cut answer, and it totally depends on the scenario. And you can probably think of other scenarios that are more pernicious. And then finally, machine learning is not something you use in isolation. A lot of vendors talk about it like it's the be-all, end-all. Typically, when machine learning is used in a system, it's one part of a number of different techniques that are used to find malicious behavior. So if you're trying to evaluate whether or not a machine learning system is going to be good, you have to look at the additive value of that approach on top of everything else you have. So typically, you'll have some blacklists and some whitelists, which we know aren't perfect, but they do a pretty good job of all the popular stuff. And then what's left over might be looked at by a machine learning system or by some other technique. So the real criteria is not how do you do on the whole data set. The real criteria is how do you do on the data set that remains once some of the other techniques have been applied. It's really critical to look at that additive value. And there may be cases where you have a machine learning system with a 10% detection rate, which sounds awful, but if it detects the 10% of things that were missed by everything else, that's actually pretty good. So you've got to look at things in context. And by the way, the opposite is true as well. You may have a detection system, a machine learning system that has a 90% detection rate, but if it's detecting the same things that all your other techniques could detect, it provides no additive value. So given that, what else is wrong with machine learning when you apply it in real life? The other thing is that in real life, when we talk about cybersecurity, we're not dealing with a static threat actor. We're dealing with adversaries who adapt. We're dealing with people who literally are thinking about how to get by the systems we create. And by the way, the rate at which they get by is almost a direct function of how much a threat you are to them. So you know, I've seen it. When I've been at big vendors, or if you have a lot of customers, we'll see threat actors adapt within weeks of any new technique we publish. If they figure it out, they usually are very quick to adapt and make the changes they need. The second thing is that typical machine learning algorithms, if you look at all the academic literature, they don't assume that you're dealing with a malicious scenario. They typically assume that everything is sort of hunky-dory. You've got this data set, you're trying to learn from it, you're trying to apply it. But in real life, in cybersecurity, we're dealing with threat actors who are specifically trying to circumvent the algorithms that are being created. They're going to try to fly just under the radar. If they know your threshold is X, they're going to try to be at X over 2, and so on and so forth. So they are very, very careful in what they do. Now, that doesn't mean all is lost. There are some ways of trying to address that. For example, you can take your machine learning techniques and try to make them work with more weight on the later data set so that you can try to adapt more quickly. You can try to introduce new data. You can try to do rapid retraining or relearning, so reiterating quickly on what your machine learning algorithms are doing, the cadence at which they're being applied. You can also potentially try to do something called online learning, where every time you see a new example or a new instance, you try to retrain your classifier based on the latest data you're seeing. Now, again, that's not perfect either. I'm sure we can come up with 72 different ways to break that. And in fact, this is an area of active research. There's in fact a whole field of machine learning called transfer learning or inductive learning that tries to look at the problem of what happens if you're trying to develop a machine learning system that's applied for one setting, and then you're trying to make a small change in the rules of the game and apply it to a different setting. So for example, they've tried to do this for games like Go, where they might try to design a machine learning system that works for Go on a 15 by 15 board, and then they'll try to see what happens if they take that same system and make it work on a larger board. That's something humans are pretty good at. We're pretty good at being able to adapt to slightly different scenarios with limited data, but machines are not good at doing that. And to this day, the literature in this area of inductive learning and transfer learning has shown some early promise, but I think there's a huge way to go before we can make this stuff work in real life. But it's very, very pertinent for our industry. Supervised learning also has pitfalls specific to it. So for example, the training set in supervised learning will typically capture what you know about, right? It's all the stuff that you were aware of in the past, which means the models that you generate from that training set might draw some additional inferences, but will only slightly expand your state of knowledge. And what often happens is people develop these really cool looking models, and what they end up with at the end of the day is kind of a glorified signature. It's basically maybe a bunch of if-then statements, looks at some byte code, but nothing much more beyond that, if they're not careful at least. It's really important to realize that we're dealing oftentimes not just with the things we know about, but what I like to call the unknown unknowns, right? The things that we don't yet know about, which is really why we're trying to apply machine learning in the first place. So again, it may give you some mileage, but may not be as much as you think. On the flip side, again, malicious behavior is subjective. And whether or not something is malicious is less about what that tool is and more about how it's being used, what the intent is. So for example, PowerShell. We've seen PowerShell. PowerShell has good uses. We see a lot of bad guys use PowerShell as well. You can't develop a machine learning algorithm that tries to classify PowerShell on its own. What you've got to look at maybe is how it's being used and whether or not that use is actually malicious in intent. And that's something that's really hard to do. There may be cases where somebody is legitimately allowed to transfer a lot of data out of your data center. They're allowed to, they're doing it for a specific business purpose, the intention is good, but you put somebody else in there who maybe has a bad intention and who's not supposed to transfer that data out, and all of a sudden the intention becomes bad. If you look at just the behaviors alone, the behaviors look identical at a high level. It's the intent that might be different. And intent is something that's very, very hard to measure computationally. I don't know that any computer can be a good moralizer in our lifetimes, but it's an open area of research, and maybe that's something we'll come up with at some point. But for now, that's a fundamental limitation of machine learning. Now, what I want to point out is that machine learning is not all that bad. The reality is there's a lot of low-hanging fruit out there that people have not been picking for a long time. Machine learning is great at being able to identify some of that, expand our horizons a bit. It definitely moves the needle on being able to do a better job of threat detection, but it may not move the needle as much as you might read about in a vendor white paper. So it's really important to put some context around that, take it with a grain of salt. Now finally, I'm going to talk about a story that happened to me personally that I think illustrates this point. A number of years ago, I was working on a project involving file reputation. So I was working on how to do automatic file reputation using a lot of data that I was looking at and whatnot. And as any good technologist or engineer likes to do, I started working on a side project which I thought would be kind of interesting. I had all this data on file reputation. I wanted to see if I could apply that data to certificate reputation. Can I figure out something about the digital certificates that were being used to sign the binaries associated with the files for which I had reputation scores? And the idea was the following. If I have a bunch of files and they've got high reputation, then I can kind of infer that the corresponding certificate that was used in digitally signing those files should also have high reputation, which then would lead me to believe that anything else signed by that same certificate should likely have high reputation as well. So it was a way to use something about file reputation to determine whether or not I could infer something about certificate reputation, and then in turn use information about certificate reputation to then infer something about file reputation. And machine learning was at the core of this system. So I started doing this for file reputation. When I tried to apply it to certificate reputation, I started collecting a lot of data, as I would typically do. And so I had a bunch of data on certificates, I had a bunch of data on files, and I was trying to just play with some ideas. So I put my data on a spreadsheet. I had maybe about 30 or 40,000 rows at the time, and I kind of reduced it down to just a handful of interesting certificates. And roughly speaking, the certificates kind of fell into one of two categories. The first set of certificates were only being used to sign popular stuff, really high reputation files. Think of things like Microsoft or Adobe or something of that nature. Everything those certificates were signing were really popular, really high reputation, nothing strange or weird. On the other hand, I also saw some certificates that were being used to sign a lot of low reputation files. So things like adware vendors very typically would sign their binaries, but you could tell that they were adware vendors because the binaries being signed were all kind of one-offs, not very popular, and whatnot. But there was one line on my spreadsheet that was kind of throwing me off, and it was line 23. I vividly remember it. And this was a certificate that was being used to sign some good things that were very popular and had high reputation. It was also being used to sign some things that were very, very unpopular, had maybe one or two instances in the world. And that struck me as kind of weird. Why would a legitimate software company sign something but only give it to maybe one person, but do that 300 times for 300 different people? So I couldn't make sense out of it at all. I concluded maybe there's something wrong with my data. At some point, I think I left the company, forgot about the project, and kind of moved on with my life. And a few months later, I was sitting there and read a report about a threat that we all heard of, hopefully, Stuxnet. Now, what's interesting is Stuxnet was digitally signed. It was digitally signed by the real tech certificate, which was line 23 of my spreadsheet. So here I was, okay? Nobody knew about Stuxnet when I first looked at the spreadsheet, okay? And I was staring at it in the face. It was literally in front of me. I could see tons of binaries being signed by it. In fact, a bunch that never were talked about publicly at the time. And I missed it. And I had background in malware analysis. I was in security for a while. I thought I was a domain expert. I was very humbled by that experience because I realized, hey, for everything I knew, here were these threat actors who completely threw me through a loop. And I completely ignored it. I missed all the warning signs. It was months later before I finally put all this together. And I bring this up because this is really why machine learning is hard to apply in real life. You know, we're not dealing with a threat actor who's only going to sit there and make one change and throw a piece of malware out there and never change it again. They're specifically going to try to mess with you. And machine learning still hasn't figured out how to deal with that effectively. Now, it's not that you can't apply it and move the needle, but you've got to be cognizant of the fact that there are going to be certain things that will be, for the foreseeable future, beyond the scope of what machine learning can accomplish. I want to share also with you some pitfalls of unsupervised machine learning. These are somewhat obvious, but I think it's important to note. The reality is that people don't realize that when you look at unsupervised learning, it's really about being able to find things that are out of the norm. And something being abnormal is not the same thing as being malicious. For example, I'm here today at the Annenberg Beach House. I've never been here before in my life, I can assure you. You know, some machine learning system might be tripping up somewhere if it finds me here because it's an anomaly for me. Right? So anomalous behavior is not the same thing as malicious behavior. There may be reasons why you behave anomalously. Maybe you're traveling. Maybe you have a work deadline, so all of a sudden you're checking in and out more code than you normally would. Maybe there's a holiday sale at the website that you're monitoring, and all of a sudden they see a spike in traffic that's abnormal. Normally abnormal, but is actually perfectly reasonable within the context of a sale. And so it's really tricky. You've got to take into account not just what you're putting in, but you've got to take into account whether or not the context suggests that that data should look at the way it does. Then finally, it's actually not that easy to measure normal behavior if you're trying to look at logs and whatnot. So for example, I've seen a lot of companies try to look at geolocation behavior and look for geolocation anomalies like, hey, why was Zuli in China, and then a second later in California, and a second later somewhere else? That's all fine and good, but geolocation is baseline hard to measure. I could use a MiFi device. I could use a VPN. All those things will typically throw off geolocation-based solutions. And so it turns out that if you can't measure the data accurately, and it's hard to tell whether or not something is truly malicious versus abnormal, it's very hard then to make inferences beyond that. Not even a human could potentially do it, let alone a machine learning algorithm. So there are some fundamental pitfalls in trying to make machine learning work in the real world. And really the moral of the story is that actions themselves are not the same thing as the intent behind those actions. What we're trying to find out in our field is the intent, not the action. And you've got to account for that when we think about how to build machine learning systems for dealing with those problems. Now I want to talk about one final topic, which is you've worked on a really great machine learning system. It looks great on paper. At some point, you've got to push it out to a customer or put it in the field. We've got to deploy models. And people kind of forget about this part, right? They think that everything looks good, but there's a subtle aspect of DevOps that's associated with machine learning. And in fact, this may be a ripe area for this community to think about, is how do you actually think about DevOps in a machine learning context? Here's a great example. Okay, machine learning produces models. That model's got to be deployed. So you need some way to vet whether the model being deployed is going to do a good job. Of course, if you had a way to tell whether the model being deployed was going to do a good job, then it would be much easier to come up with those models. That's the challenge of coming up with a good model. But it turns out that there are situations in which you can take a model that maybe looks like it makes sense when you start with it, but somehow you've got to figure out whether that real model is going to work in real life. So for example, let's say that you're trying to find, actually I saw this happen in real life once. Somebody I knew was trying to develop a model for trying to detect malware, and they applied machine learning and they used a library. And somehow the model picked up on the fact that you could use the compile times for the binaries to figure out whether or not something was malicious. Here's a hint, that probably won't work in real life. That probably worked really well in his data set, but it's not the kind of thing that you could apply in the real world. Now, if he just went ahead and blindly put that, he actually did go ahead and blindly put that model in real life, that's a different story. But if he took a look at the model and spent a moment looking at it, he would say, well, obviously the compile time shouldn't be a critical factor in determining whether or not something is malware. So if I've got a model that's really heavily dependent on the compile time, it's probably not the right model. It's a subtle point, but you've got to find a way to determine whether or not the model makes sense. Is the model something that's going to do really well in your training set, which in that case it was, but do really poorly in real life? And more importantly, let's say you do put the model in the field. At some point, if a customer support issue comes up, the person looking at that issue may not have a PhD in machine learning. They may not understand the importance of maximum margin separation or deep neural networks or any of that thing. What they really care about is, hey, how do I fix a customer issue? To do that, they have to be able to understand something about what was put in place. But if the model is so complicated and hard to understand and there's no context, that's really, really hard to do. So it's really important to understand that from a support context, you've got to figure out how to deal with machine learning and make things work. And by the way, that thing I talked about earlier about data, then features, then model, that's a good reason to pick a simple model, because you want something that can be understood potentially by someone who does not have a machine learning background in the field. So given all that, I want to kind of quickly summarize the key issues here. We talked about why machine learning, I think, is a very good tool for cybersecurity, but on the flip side, does have a number of caveats and pitfalls associated with it, and that there are some realities to understand, and you've got to be able to figure out when the hype fails to meet the reality. In terms of best practices, start off by making sure that you focus on data first, then features, then classifier. If you're spending all your time looking at the features and classifier but not the data, you're doing something wrong. And if you're spending too much time tweaking parameters in your machine learning library, you're definitely doing something wrong. The second thing is you have to know what success means. It's not just about having a high true positive and a low false positive. You've got to understand what that means in the specific scenario to which it's being applied. Because not all those metrics are created equal, and they may be completely dependent on the scenario you're dealing with. Third, don't set it and forget it. Real-life threat actors do adapt, right? They're trying to pay attention to what you're doing, especially if you're big, and they're trying to figure out how to modify their behaviors to get by them. They're trying to fly just under the radar. If they understand that you will, and by the way, Stuxnet was a great example, a lot of antivirus vendors weren't calling things that were digitally signed by Class 3 certificates malicious. And so threat actors figured that out, and they found a way to compromise a Class 3 certificate and sign something with it. They're trying to adapt their behaviors. You can't just set it and forget it. Then finally, you've got to think about how to put those models in the field successfully, and realize that the person putting it into the field may not be the same person who developed it, and typically will not understand all the nuances of what that model might mean. And so as you start to develop models in machine learning, you've got to think about how to make the model maybe sufficiently simple, or provide some of the right context or explainability so someone can actually triage an in-field issue. So with that, I think machine learning has a lot of promise. I don't want to make it seem like it's all negative, but I want to make sure that we provide a balance here, because you can go out to any vendor booth and read a white paper and get the positives of it. A typical vendor won't tell you where it might not work. But at the same time, machine learning has been used for a long time. I guarantee you that most of the major cybersecurity vendors on the planet have been doing it successfully and moving the needle with it. But I think that you have to be careful with the hype versus the reality. So with that, I want to try to get you guys back on track for today's lunch. And I hope you had a good time with the presentation. Thank you all very much.